Hi, class. So this is our second lecture in chapter 17. This will be on 17.2 on galvanic cells. And like the previous chapter, there's no math. There are no equations to solve on this one. It's qualitative and it's description of cells, electrical cells that produce electricity from redox reactions. So I'm going to start my slideshow. So we'll start from the learning objectives for chapter 17.2 on galvanic cells. So let's describe the function of a galvanic cell and its components. That's the first thing. What does it do? Why is there such a thing? And then secondly, let's use cell notation to symbolize the composition and the construction of organic cells. So there's a shorthand we can use that to describe galvanic cells. And galvanic cells are the function has to do with producing electricity. So if we combine these redox reactions in the right way, if we do the right thing with them, we can actually produce electricity, which is electrical work. We can produce work with that. And later on in this chapter, we'll learn how to calculate the free energy that these will produce. And that's later on in chapter 17.4. So let's look at a redox reaction. This is one that we've looked at several times. In this case, it says when a piece of copper metal is added to a silver ion solution, we get this reaction. And if we do it in a test tube, it's a spontaneous reaction. So the silver metal is deposited on the surface of the copper wire. Copper enters the solution as blue copper 2+ ions. We saw this reaction previously in chapter 17.1. And so on the left, we have the copper wire and the silver solution, which could be silver nitrate. It's a nice solution to use. And then when you put the copper wire in the silver nitrate solution, right away the solution turns blue because that's from the copper 2+ ions. They're blue. And the copper wire starts turning black because the silver starts depositing on the wire. So galvanic cell. So what's a galvanic cell? How do we make something useful out of this reaction? Well, first of all, any spontaneous redox reaction can serve as a source of electrical energy in a galvanic cell. So as I said before, galvanic cells are used to produce electrical energy. Galvanic cells, you know what they are? They're batteries. That's what batteries are. Batteries are galvanic cells. Later on in this chapter, on sections that we're not going to cover, they talk about various batteries made from redox reactions. So if you're interested in batteries like mercury batteries, lithium batteries, those lead sulfate batteries that are in automobiles, the construction of those batteries is described later in this chapter. So you might want to look at that if you're interested in it. So anyway, the cell design, these so-called galvanic cells, take advantage of the movement of electrons that occurs during a redox reaction. And that's where the energy comes from. So the way we do this is that we compartmentalize the reactions that are going on. So we have two compartments. In one compartment, we have the oxidation reaction, and that compartment is called the anode. And in the other compartment, we have the reduction reaction. That's called the cathode. Now, if we put a wire between these two, the electrons will flow from the anode, where oxidation is taking place, to the cathode, where reduction is taking place. And these moving electrons are a source of electrical energy. So what does a galvanic cell look like? So in this slide, I have a schematic. It's just a drawing of kind of a general drawing of what they look like. And there are rules for drawing these. So you just don't draw them at random, like putting, you don't do the redox or the oxidation reaction wherever, or there's a systematic way of drawing these cells. And so on the left side of your diagram is called the anode, and that's for oxidation reaction. So the anode, we have a chamber here that contains the ions that are being produced, or the solution, whatever's in solution. We have an electrode that is called the anode. We have this other thing called the salt bridge. And then on the right side, we have a compartment called the cathode, where the reduction reaction is taking place. And we have an electrode in this side. So the electrodes are connected by a wire, and this is where the electrons go through. In between, along this wire, you can have a voltmeter. They tell you how many volts. That's the potential energy that's being produced by this electron flow. And you could have, but instead of a voltmeter, you could have an electric motor that would be running. You could have a light bulb. There's lots of things that you could have in that you could get the work out of this electron flow to produce work. The other part of these cells is that the cells have to be connected by this thing called a salt bridge. So in this diagram, the cells are separated, the anode separated from the cathode, and there's this salt bridge that's joining them. In the actual construction of a battery, sometimes the anode and the cathode are really close together. The salt bridge can be a membrane, for example, just for, it doesn't have to be the salt bridge. But if you're doing a liquid cell, you have to have this salt bridge. If you're setting it up, and I think you might construct something like this in lab. So anyway, this salt bridge helps to balance the ionic charge in these two cells. So you have ions in solution. Well, as the reaction progresses, you produce more ions on one side than the other side. And what happens is, I'm going to draw on the screen, is that you have a negative ions always flowing to the anode side, because you're losing electrons from this side. So you're losing negative charge from this side. So in the salt bridge, you have negative ions going to the left. I'll try to draw that. So I would say, I'll just put something in negative charge. So we have some negative charge going this way, always, in this salt bridge. And we have positive charge going this way in this salt bridge. And so you can think of it that on the anode side, it's oxidation, so we're losing electrons. So this negative charge replaces the electrons. The charge of the electrons is being lost. And on the right side, let's see what happened to my mouse. So on the right side, we have electrons ending up over on the right side. So we have this positive charge from the salt bridge that neutralizes those electrons on the right side. So it balances the electrons. Now, a couple of things can happen on the right side. Sometimes electrons are coming over, but we have positive ions in solution that are being depleted. So the positive ions are disappearing because these electrons keep coming in to solution, and this positive ion from the salt bridge replaces that. So that's described in your book about what the salt bridge is doing. But basically, you have negative charge going to the anode, positive charge going to the cathode. That's what the salt bridge is doing. So let's go to the next slide. So if we separate the half reactions and force these electrons to pass through So what if we separate these half reactions and force it to go through an external wire? Well, that's what's called a galvanic cell. So let's look at our friendly redox reaction or copper wire and silver ion solution. That's a spontaneous reaction, we saw it before. So the way we're going to build a galvanic cell out of this, we'll put the copper wire, say, into a solution of copper ions. And because the copper is being oxidized, this would go on the anode side. So that's going on the anode side. And here's the chemical reaction that's occurring on the anode side. We have solid copper going to copper ion plus 2 electrons. This happens on the anode side. And then on the cathode side, we have a silver metal electrode that dips into the solution of silver ions. And this is the reaction going on the cathode side. So the silver ions are capturing these electrons coming over from the copper, producing silver. And then there's an external wire that connects the electrodes, that connects the anode with the cathode. And if you pass this through a voltmeter, you see how many volts are being produced. And in the next section of the chapter, we're going to calculate be able to calculate the volts from this kind of galvanic cell. So what would it look like? So this is more of a picture of what the cell would look like. And in this particular cell, you can see on the anode side, we have a copper metal anode. And in the solution, we have a nitrate ion, which could be copper nitrate, copper 2 nitrate. So you'd have a solution of copper 2 nitrate. So you have to have the ion and the electrode present. You just can't have the electrode sitting in a solution of water. So you have a solution of the copper 2+ ion and the copper electrode immersed in that. Typically, real common, we're going to talk about standard cell potentials. And in a standard cell, the concentration of the copper 2+ would be 1 molar. And then you have this salt bridge, which is full of sodium nitrate. So that's an inert substance. So sodium ions don't do anything. They're not involved in the reaction. The nitrate's not involved. So you just need some inert salt. So sodium nitrate, sodium chloride, sodium sulfate would be good. So things like that. The book has a few examples of salts that are used in this salt bridge. In this case, it's sodium nitrate. And you can see in this salt bridge, the nitrate ions carry the negative charge, and they're going into the anode to replace the electrons that are being lost. And on the cathode side, the sodium ions are going into the cathode to replace the silver ions that are being lost. So what's going on the cathode side? Well, the cathode side, if you remember the reaction, is silver ion plus electrons, or 2 silver ions plus 2 electrons produces silver. So silver is being deposited on the silver electrode. So here we have a silver cathode electrode, and the silver ions are being deposited on that. Electron flow is going from the anode through a device. It could be a light bulb. It could be says an external circuit. So there might be a circuit here that's going to a light bulb or going, someplace to run an electric motor or something. But the electrons are going from the anode over to the cathode. All right, so that's what a galvanic cell looks like. Those are all the parts of a galvanic cell, or a galvanic cell. So you have to have electrodes, an anode electrode, a cathode electrode. You have to have an anode cell, a cathode cell with solutions in it. You have to have a wire connecting them. You have to have a salt bridge. So those are like all the parts. You don't have to have a voltmeter or a motor that's being run by these electrons. You don't have to do that. But if you want to capture the energy that the cell's producing, that's how you would do it. You put something into this wire that would capture the energy being produced. So I guess the other point, let me go back to that one. The other point is that the salt bridge completes the circuit. So you have to have a circuit in an electrical system. So it keeps the circuit. It also keeps the charge balanced in these cells. So you have charge balance, and you have a completed circuit. So as the oxidation occurs, you get a surplus of positive ions on the anode, and those extra positive ions produced by the copper 2+ ion are balanced by the nitrate. Remember, there's nitrate coming over from the salt bridge. So you can say that the copper 2+ ions are building up because the copper atoms are losing 2 electrons. So that's producing 2 copper ions. And so the nitrate's coming over to neutralize those extra copper ions. Then on the other side, you have a deficient in positive ions because the silver ions are disappearing from solution. And so you have the sodium ions from that salt bridge replacing those. That's what this slide is about. The salt bridge is a porous material consisting of a concentrated salt. It could be sodium nitrate in this example, or potassium nitrate. It could be, I think, sodium chloride or potassium chloride. So anions flow towards the anode, and cations flow towards the cathode. So this always happens. It doesn't matter what reaction's going on, but because oxidation is taking place at the anode, and so, like I said, you're losing electrons. So that charge that's being lost has to be replaced by the negative ion in the salt bridge. So anions flow always towards the anode, and cations, the opposite is true for the cathode. So cations are always going to the cathode. So the last statement tells you what the salt bridge does. The flow of ions enables electrical neutrality to be achieved, and also the circuit to be complete, and current to flow. So here's the same cell, summary of that cell with all the parts explained now. So if you have any questions, be sure to drop in at office hours and let me know, or ask your tutor, KJ. She can help with this too. So the summary of a galvanic cell, it's compartmentalizing the redox reaction, half reaction, into separate cells. So we take each half reaction, and we put a half reaction, the oxidation half reaction in the anode cell, and the reduction half reaction in the cathode cell. And then lastly, the half cells have to be joined by an external wire and a salt bridge. Okay, so there's something else we can do though. We don't have to draw a picture of a cell all the time. We can write a notation that describes a cell. So that's what this slide is about. So the cell notation is summarized right here at the very top. So I'm going to start drawing on this slide again. And so here's the cell notation. I'll just outline it right here. This is the cell notation. And you start from the left side and you write the anode, the actual chemical symbol for what the anode is made out of. And then next you put the anode electrolyte, what is in the solution. And then you could put down the chemical formula for the salt bridge. Next would be the cathode. As you go from left to right, you write everything down for the anode, and then you write the salt bridge, and then you write the cathode electrolyte, and then finally the cathode material. Now, sometimes the anode and the cathode aren't materials that are in the chemical reaction. In that case, you're going to have to have another line here. You might have an inert anode or an inert cathode. And inert materials are electrodes that they have to be able to conduct electricity, but they're not involved in the chemical reaction. And so get my mouse back here. And so substances like that could be like platinum is a good electrode, platinum, or gold. Gold's kind of expensive, both are platinum. Graphite is often used. Graphite's a cheap material. So in fact, in um, the alkaline batteries that you find in flashlights and stuff, those have graphite electrodes. So if you have if the anode is graphite, then usually the electrolyte may have two soluble substances that are undergoing oxidation and reduction. So if you have two electrolytes or two soluble salts that are, say, Fe3 plus going to Fe2 plus, so that would be reduction. Well, reduction's on this side. But if you have Fe3 plus going to Fe2 plus, you would put the Fe3 plus, comma, Fe2 plus, and you write them in the order that the change is occurring. So if it's reduction, you'd write the Fe3 plus to Fe2 plus on the cathode side. If it was oxidation, you put Fe2 plus to Fe3 plus on the anode side, and they'd be separated by a comma. The salt bridge, sometimes you write the formula for the salt bridge, and sometimes you don't. You don't have to. If you don't write the formula for the salt bridge, you just put a double line in between the cathode and the anode. And so anyway, this cell notation describes what's happening in the galvanic cell. Anodes on the left, cathodes on the right, just like our diagram. Oxidation in the anode, reduction at the cathode. So in this case, on the left side, we have copper going to copper 2 plus. So that's what we'd have here. The anode's copper. The anode electrolyte is copper 2 plus. Salt bridge could be sodium nitrate. That's what it shows here. We could write that in. On the right side, we have silver ion going to silver. So it's Ag plus going to Ag. That's reduction. And then the cathode is Ag. So we would just have Ag plus going to Ag. If you had, like I said, if they're both soluble electrolytes undergoing the reduction, you'd have to write it both there. So anyway, at the bottom, we have the notation for this particular cell, so it's not that complicated. It can be more complicated, but in this case, it's not. So what we have is, let me go back, come on. Okay, here we go. So here's our notation, and on the left is what's going on at the anode, and on the right is what's going on at the cathode. So I'll just write here, this is the anode side, this is the cathode side. And the anode, typically, if you want to do in a battery, the anode is the negative side. Remember, in batteries, you have both negative, you have a negative pole and a positive pole, negative side and a positive side. Well, anode is a negative side. So this is, let me go back. And I'll draw this again. So the anode is negative, and the cathode is positive. All right, let's go on to the next slide. So this is an example. So this is a different one. So let's build a galvanic cell based on the spontaneous reaction between copper 2 plus and zinc 2 plus ions. So the spontaneous reaction, first of all, you have to know what the spontaneous reaction is. So let's see what the spontaneous reaction, what's going on here, come on. Okay, I lost my, there we go. All right. Not sure what's going on. There we go. Finally, spontaneous reaction in this case would be zinc plus copper 2 plus going to zinc ion plus copper. So we'd want to separate the oxidation and the reduction. This is the spontaneous reaction. Now, later on in this chapter, in fact, in the next section, we're going to be able to decide when you have a redox reaction, which one, there's a depending on something called the reduction potential, you'll be able to determine which half reaction is oxidation or which direction is spontaneous. So we can always write a redox reaction, but you don't know which direction it's going to go spontaneously. And remember, a spontaneous reaction has a negative free energy. So that's coming later too. We're going to calculate the free energies for these spontaneous reactions. And but anyway, if you don't know what the spontaneous direction is, then you have to be given that. So what is being oxidized? In this case, the zinc is being oxidized, so we know that that goes on the anode side. So you know the other reaction is reduction, so that goes on the cathode side. So let's write the cell notation. So on the anode side, we have a zinc solid electrode. That's a metal, so that would make a good electrode. So we put zinc as the anode. And then we have in solution, we have zinc ion. And that could be zinc chloride, for example, or zinc nitrate. And then we have a salt bridge. So we haven't specified a salt bridge. And then on the right side, in solution, next comes the solution on the cathode side, is the copper 2+ ion. And that could be copper nitrate, copper chloride. And then as a cathode electrode, we have copper, solid copper metal. Right, so there's a notation. So once we have a notation, we can build our cell. So let's build our cell. So the first thing you want to do is sketch a cell diagram. So the cell diagram kind of looks like this. So we have an anode side, a cup, you could say, that holds our anode electrolyte with an electrode and a salt bridge in it. Then on the right side, we have a cathode, a cell that has a cathode solution. And again, on the cathode side, we need a cathode electrode, and also the salt bridge is in there. So that's our template. So this is what we call a template for a galvanic cell. So that's the first thing you want to sketch is a template. Next, you want to add symbols for the electrode and cell solutions on the anode side and the cathode side. So on the anode side, we have a zinc electrode. So you could put the Zn here. I wrote in zinc electrode. You could Zn, that's the electrode. And then the solution, we have zinc ion. And then on the cathode side, we have copper ion, and we have a copper electrode. So that's how you would diagram a galvanic cell for this reaction shown in number 1 here. So this is what we're going to do in our worksheets. So let me stop my slide share. And stop the share. Come on, there we go. And I'm going to switch over to my camera, and we're going to do worksheet 28. So here we go. So worksheet 28 is kind of a long, 6 pages. So sorry about that. The actual problems are on the last 3 pages. The first 3 pages describe what we just went over in this lecture. So this is a good summary. It's pretty much a summary of what you'll find in section 17.2 of your book. So I'm going to skip over this. The example in this summary is the example that I went over in the lecture. So it was the zinc plus copper 2+ to produce the zinc ion and copper solid. So this is the spontaneous zinc copper 2+ reaction. If you want to do this in lab and watch it occur, you could just put the zinc metal into a copper 2+ ion, which is blue, and the blue color would disappear, would fade as the copper 2+ disappears, and the zinc metal would dissolve. It would just go away as the zinc 2+ ions are formed. Second page talks about what's going on in the electrochemical cell or the galvanic cell. Okay, so I'm not going to go over that. We just went over that in the lecture. And then the third page is an example of how you would take a spontaneous reaction shown here, magnesium plus iron 2 ion going to magnesium ion plus iron solid. and separating it into the oxidation reaction and the reduction reaction, and then sketching a electrochemical cell for that reaction, and then writing the cell notation. So that's the 3 steps there. Now, what I want to do is, I wonder if I should make this bigger. Let me make this bigger. Maybe that helps. I don't know if that made any difference from your angle or not. But there are 3 problems now. The next 3 page has 3 problems. So I'm going to go to those. I'll do the first one. And then I want you guys to do the other 2. And this is a worksheet I want you to turn in. So I'm going to put right here, turn in this worksheet. Turn it in. So let's go to this. So it says, here's the following reaction, and this is a spontaneous reaction. It's iron solid plus copper, 2 plus ion, in this case copper sulfate, going to iron 2, or iron sulfate plus copper solid. So this first thing says balance this equation. So to write to sketch a galvanic cell or to write the cell notation, you don't have to necessarily have a balanced equation. So what we're just showing is oxidation and the reduction. But we're going to balance this equation anyway, just for practice. So in this case, if you look at the reaction, it looks like we have 2 irons on this side, 3 sulfates and 3 coppers. And so we need, I think, to balance it, if we do 2Fe plus 3Cu SO4, and I'll put in my subscripts here just to be complete. And then we're going to go to Fe2SO4 3 plus 3Cu solid. Okay, so there's our balanced reaction. So write the net reaction. So in this reaction, the sulfate's not doing anything. So the net reaction is going to be 2Fe solid plus 3Cu2 plus aqueous is going to 2Fe3 plus aqueous plus 3 copper solids. Now the importance of the balanced reaction is later on, you're going to have to know how many electrons are being transferred in this reaction. So in this reaction, we have 3 copper 2 plus that are going to copper solid. So we know that we're going from a 2 plus copper to a 0 copper. So you look at the oxidation numbers, and the copper, each copper ion is gaining 2 electrons. So there's 3 of them. So we have 6 electrons. So the copper is picking up 6 electrons. And in turn, the iron has to be giving up 6 electrons. So that means each iron atom is giving up 3 electrons, because we know it goes from iron 0 to iron 3 plus. So with 2 iron atoms, that means 2 times 3 gives 6 electrons that the iron atoms are giving up. So in this reaction, we're transferring 6 electrons. Now, that has a big impact on how much voltage we're going to produce. The amps, watts, voltage, they're all connected. So the flow of electrons equal to the amps. That gives you, in turn, you can calculate the energy in watts, and the potential called volts. So we're going to do that later. But that's the purpose of the balanced reaction, is to be able to know, calculate, determine how many electrons are moving from the oxidation to the reduction side. So let's write the two half reactions. So if we write the two half reactions, that becomes obvious. So we're going to split this net reaction into two. And when we split this into two, the number of electrons moving becomes clear. Okay, I didn't write that correctly. Let me fix it. There we go. I put the electrons on the wrong side, but that's okay. Can always fix that. So we have going from iron 0 to iron 3 plus. We have 6 plus on the right side and 6 minus, so that charge equals the right side. This is oxidation. Of course, when you're writing oxidation half reaction, the electrons have to be on the right side because the half reaction is producing electrons, right? And this will be at the anode. So all those go together. Electrons are are a product of the half reaction that makes it oxidation. So the reduction is the opposite. So we know that on the reduction side, we have 3 copper 2 plus ions, and we're going to have to add 6 electrons. So this is reduction. And that's going to give us 3 copper 0 copper with a oxidation number of 0 solid on the right side. So there's our two half reactions. So write the cell notation. So the cell notation is pretty easy now. So the cell notation is going to be iron, and we don't put in the stoichiometry when we write the cell notation. So we have solid iron as an electrode. We have iron 3 plus in solution, so that's aqueous. In the solution, we have our salt bridge, and then we have our copper in solution, copper 2 plus aqueous, and then we have our copper electrode on the cathode side. So anode side, cathode side, there's our solution. So now let's draw our cell diagram. This is probably going to take longer. So the cell diagram, the first thing, I have a little template here that's going to help me draw the cell diagram. I'm going to draw a salt bridge first. So I have my little tool here. I like to draw the salt bridge first so that I can there we go. Here's my salt bridge. Okay, that's the salt bridge. I'll put an SB salt bridge there. Oh, can't see that. Okay, here we go. There's my salt bridge. And then on either side, I have on the left side of the salt bridge, I have to have a anode. So here's my anode. And on the right side, I have to have the cathode. So there's my cathode. And then inside this anode and cathode is an electrode. So here's an electrode. Here's one electrode, and here's the other electrode, right? And my salt bridge, and then I have a solution in here. So the electrode, so I'll have my solution is like this. Maybe I'll extend this salt bridge down a little bit. There. So here's my solution. And then these electrodes then are connected by a wire. They have to be connected by a wire. So I'll draw a wire here. And then here's my wire. And then here's another wire going this way. There. And then right here at this wire, I'm going to connect these wires to something. So I'm going to put a little connector here. And this wire is going to be connected to I'm going to put a light bulb in here. So here's my little light bulb. So my light bulb looks like this. Okay, this is my light bulb. And so there's my basic cell template. So now I've got to fill in the parts of this cell that come from my cell notation. So the anode, this is the anode side, anode, cathode. And my anode electrode is going to be iron, solid. And my solution is going to contain iron 3+ ion. And that could be iron chloride, iron nitrate, something like that. And on the cathode side, I'll just put in my copper ion. My copper ion. And I don't have to put the AQ because it's in water. That's the little waves here indicate this is an aqueous solution. And then on the my copper electrode, I'll just put an arrow here pointing to the cathode, and the electrode on the cathode side is going to be solid copper. So that's it. So that's what the diagram looks like. And so what I want you to do is do the same thing. These problems are not too long, but do the same thing or follow the instructions for problems 2, which is a different reaction. It's copper and tin. And in this case, use the reactions as written. So identify the oxidation reaction, identify the reduction reaction, and then put the half reactions in the correct sides. Okay, so this is the reaction here for number 2 as written. We're not going to worry about, we're just going to assume this is spontaneous as written. It is spontaneous, I know that. So that's the one you're going to use. And then for problem 3, let's see, problem 3 is a different reaction. And this reaction has a little note here to help you write it. If you notice this reaction, there are no metals involved. So the iron, you have iron 3+ going to iron 2+, so that's reduction. And you have iodide ion going to iodine, elemental iodine. And so iodine's not a metal, so you can't make an electrode out of that. So there's a little note here that says, in this case, you're going to need to use inert electrodes in both of the cells. And so when you separate phases, so one thing when you're writing this cell notation, you need to use a vertical line in separating phases. So on the iodine side, we have aqueous phase and we have an iodine phase, I2 solid phase, but you're also going to have a inert electrode also in there. So sometimes, you know, the cell notation down here where you write the cell notation might get a little more complicated. So give that one a try. And you know, there aren't any wrong answers. So do your best. And when you turn in this worksheet, I will help you out with corrections if you made any mistakes. So that's about it for chapter 17.2. So I'm going to sign off and good luck. And if you have any questions, as always, stop in at office hours or drop me a note or an email. Goodbye.